Whew, you've made it to the last screencast about complex circuits today. Whew, congratulations. All right. So you've got a slide in your notes that has this reasonably complex circuit and then three questions about it. And I've simply made another sheet that just has each one of those questions and that circuit a little bit larger. We're going to answer each of those questions. But before we do, we're going to talk about the strategies for doing this. This video is really in support of questions 11 through 14 on the series parallel complex circuits lab. And those last four questions ask you a bunch of questions about what happens to other resistors and to the whole circuit when changes are made to a circuit. And this is high level stuff. This is really applying in kind of a creative and sophisticated way your understanding about how the circuit functions. And it's a really common test question. You're going to face a couple of these at least. So just want to get you familiar with the approach. So let's first look at the kinds of questions we're talking about. So we're given a circuit here. And we can think about how this works a little bit. We've got resistor 1 in series to everything else in the circuit. So that means the voltage across any of resistors 2 through 7 can't be the total voltage because resistor 1 will end up consuming a part of the 5 volts because it will be included in any loop. So we can apply Kirchhoff's loop rule, recognizing that if we started here and ended there, that there be no change in voltage. So gain 5 volts, whatever the voltage is across resistor 1, and the voltage drop across resistor 2 and 3, that would have to add up to 5 volts so that we're back to 0 by the time we get back to the battery. We could write another loop rule for resistor 1, 4, and 5, and then back to the battery, and a different loop rule for resistor 1, 4, 6, and 7. The voltage dropped across each one of those resistors would have to be equal to 5 volts. We can also see that resistor 6 and 7 are in series, so they get the same current as each other. We can see that between here and here, there's only wire, and between here and here, there's only wire. So V6-7, the voltage across both resistors 6 and 7, would have to be the same as it is across resistor 5. We know the current through resistor 2 and 3 would be the same as each other, but it would be a fraction of the total because there are two other paths for current to flow through the circuit that skip resistors 2 and 3. And of course, we can build this in FET and get a feel for those statements that I just made and how they're true. So here's the voltage across the battery, the 5 volts. And if we measure the voltage lost across this first resistor, resistor 1, not because it happens to be the first in the path, but because it's in series, it gets a really big chunk of the voltage, 1.99 volts. That means that this chunk of the circuit, which isn't wired in series to resistor 1, can only get the other 3.01 volts, and we can see that it does. So the current through these two resistors, which is 0.25 amps, is the same through both of them since they're in series, and together they would share this 3.01 volts, not the total, because 1.99 volts has already been consumed in resistor 1 before the current ever flowed through these. And again, even if this resistor were over here, that logic would still be true. The voltage across this 10 ohm resistor up here, got the leads reversed, it's actually pretty large, 2.46 volts. Quite a lot of current flows through it, which is an indication that the resistance of this path is pretty low. The amount of current on that side is 0.25 amps. The amount of current on this one is 0.25. So that actually means the resistance that is in this chunk and the total resistance of this chunk are either equal to each other or so equal to each other that we're getting the same current to 2 sig figs. Now, we know that the voltage dropped across resistor 1 is 1.99 volts. The voltage drop across resistor 4 is 2.46 volts. That gets us awfully close to 5 volts. There's not much voltage left. So when we measure the voltage across these two resistors, man, there's that small remaining chunk, 0.55. And of course, it's the same across these two resistors. they would each share a portion of that equally because they have equal resistances. So just looking at complex circuits and thinking about how they work is a useful thing to help us to understand why the current flows where it does, why the amount of current flows where it does. And of course, we could do what we saw in the last video and just break this down to figure out everything about it without having to actually set it up or build it in FET. But what we want to focus on today is this what if scenario. So let's go back to the notes. This first question that we get is, what if we replaced resistors 2 and 3 with some wire? So if we got rid of that resistor and we instead wired from here to here with a wire, right? Now we know that the potential difference across any strand of wire is 0. So previously, the total current flowed from resistor 1, and then some of it flowed through resistor 4, and then either 5 or 6, 7, and the rest of it flowed through resistors 2 and 3. And once the current got to somewhere over here, it went back to the battery because there's nothing but wire in between, and current flows towards low potential away from high potential. Well, now the low potential, the ground, is connected via wire all the way back to the back of resistor 1. When I say to the back of it, I mean from the direction of conventional current flow. What that means is that the voltage difference between here and here would be 0. So what we'd find is that we'd short circuit this entire chunk. No current would flow. So what if resistor 2 and 3 were replaced with wire? We'd want to answer that with something like this. If we labeled this as spot A and spot B, we could say that VAB was non-zero. But if resistor 2 and 3 are replaced with wire, VAB is now 0. So R1 is the only resistor to have a voltage applied. So it would be the only thing that would get any current, and therefore the only thing that would develop any power. I'll spare you the watching me write that down. So let's go back to FET and see if that's true. FET is an awesome tool for us here, but I would encourage you to reason through what you think will happen before you model it in FET. So I'm going to go ahead and cut this resistor out and cut this chunk out as well, and we'll just move those resistors off to the side. And now we can connect the wire across, and you can see that our prediction is correct. There's no current flowing in this part of the circuit anymore. We've short-circuited that part. In this case, the short circuit doesn't cause the battery to have problems because there's still a resistor in the path. It's resistor 1, and because it's the only resistor in the path, if we think about Kirchhoff's loop rule, we'll gain 5 volts across the battery, and then that voltage will be delivered to wherever there's resistance. There's only one resistor, so it gets all 5 volts, and then the current returns back to the battery, and round we go. So when you have an electrical short, say in a car's circuitry or in a house circuitry, and all of a sudden you've got a part of the circuit that's dead, that can be sometimes happening on accident. 2 wires that are near each other, if they get jostled and over time the 2 wires insulation wears off and the metal parts of the wires touch, it'll short circuit anything physically beyond that part in the circuit. All right, 1 down. Let's talk about the next scenario. I'm going to return these 2 resistors back so we can come back here and see how it was working originally compared to the new. So back to the webcam. Here we go. So the second question was, what if we added another resistor in series with R1? So if we added another resistor in series with R1, that would be here or here. I'm going to add it down here because I want to show that it really does not matter. Either of these are in series with R1. But if you want to think about it as being somewhere along here, that's fine. The same logic will apply. Well, when resistors are added in series, remember that that effectively lengthens the resistor. If that effectively lengthens the resistor, remember that R equals rho L over A for any one resistor. And effectively, having two resistors in series is like having one resistor that's longer. Length of resistor is proportional to resistance. So increased length means increased resistance. So we've got more resistance in series with the whole circuit. Now, all of the current one of the things you want to do when you play the what if game is think about what does that do to the resistance of that chunk, and then what does that do to the resistance of the overall circuit. So resistance added in series increases the resistance of that chunk, which means that it's going to increase the resistance of the whole circuit. So from a total circuit perspective, we know that the total voltage over the total resistance will predict the total current. We've reasoned through, based on how this resistor will be added, that the resistance total goes up. That's inversely related to current, so current's going to go down. So total power is going to be decreased because less current is flowing, so less energy will be delivered in any unit of time. Total resistance will go up because we've added that extra resistor in series, effectively lengthening the resistive material the current has to flow through, and total current will be down. Now, if we start thinking about how that affects all of these resistors, this voltage will have to be smaller than 1.99 volts now, because the loop rule used to be R1, R2, R3, and now it's R1, R2, R3. We'll call this R8. So the voltage is split four ways. You could have the same logic with any of the other loops. We used to have voltage dropped across resistor 1, 4, and 5, and then back to the battery. But now it's resistor 1, 4, 5, and 8. So we're splitting voltage four ways instead of three. This old loop around this way used to split the voltage amongst resistors 1, 2, 6, and 7, but now there would have to be some voltage for resistor 8. So that means the voltage applied to any of the resistors is going to go down, which is consistent with there being less current flowing in the circuit. If there's less total current flowing here, then that makes sense that as it divides down the different branches, there'll also be less current in any of the resistors. So the net effect of adding this resistor in series is that less voltage will be applied to each one of the resistors and less current will flow through each one of the resistors. If they were light bulbs, they'd all get a lot dimmer. Let's go to FET and verify that that's true. So I've created a little junction here already where we can insert that resistor, and we can see that the current flowing in the circuit was 0.5 amps. Now it's only 0.36. The current between these two branches is still about half and half because the resistance of this branch and the resistance of this branch hasn't been changed since this resistor isn't a part of those branches. The things that we were saying before, like the current through this 2 ohm resistor and this 2 ohm resistor is the same. That's still true. It's just less current overall because the resistance of the path that those resistors are in has increased due to the increased length of this resistor being added in sequence. So we can see that a lot of these predictions are correct. We could go through and measure the voltages again. Here's the voltage across that resistor 1. It used to be 1.99. Now it's only 1.42. And the voltage across these two resistors together was 3.01. Now it's only 2.15. And again, that's because this 4 ohm resistor requires some of the total voltage since all current must flow through it. There's its 1.42 chunk. It's often useful to kind of take the what if game to its extremes. So what if we took this resistance and we really increased it? That might help us to think about how the circuit's going to be affected even better. So as the resistance of this resistor increases, it becomes a larger and larger fraction of the overall resistance of this circuit. You can kind of think of it as a 3 resistor series circuit with resistor 1. This really complex chunk has some equivalent resistance that we could find if we wanted to do a bunch of calculations, and then this resistor. So the larger the value of this resistor, the more of the total voltage it takes, and the more all of the other paths and resistors end up acting like wire because their resistance is so small in comparison to this resistor. So you can see that jacking this resistance way up really has a huge effect on the current, because a resistor in that particular part of the circuit affects the whole circuit's current, since all of the current has to flow through it. Now, I wanted to show you also, before we leave here, if we were to get rid of that resistor and reconnect here, if we had in fact added that resistor here, we do want to make sure you know it's the fact that that resistor was in series, not the fact that that resistor happened to be after the rest of them that caused that effect. So if we go back to the same 4 ohm resistor, you can see that the current we got when that 4 ohm resistor was down here, 0.36 amps, it's still the total current, even though it's up here. So it's really more about it being in series to the rest of the circuit than it is about its position, particularly within the circuit. Okay, 2 down. Let's take a look at the last one. So the last question on this page was, there we go. What if we removed the branch with R5? So if we removed this branch, now removing that branch actually takes away a path for current to flow. It takes away some cross-sectional area. I want you to think about from here to here how R5 actually impacts the resistance of that chunk. Again, really useful to think about how the resistance of that chunk is affected. So all the current from here to here would have to flow through resistor 4. But then that current can divide through resistor 5 or through resistors 6 and 7. If we remove resistor 5, that actually forces all of the current through resistor 6 and 7, which means there's less cross-sectional area for the current to flow through. So what that means is, since, again, the resistance of any chunk, and I'm really kind of thinking about this chunk now, since the resistance of any chunk is rho L over A, if we get rid of resistor 5, we're actually decreasing the area available to the current. It could flow through resistor 5 or through resistor 6, then 7. If we're decreasing the area, what that means is that we're going to end up increasing the resistance. Rho is dependent on the material of these resistors. That's not changing. L isn't really different because the current was going to have to flow through 6 and 7 beforehand anyway. That's not longer, but its area is now the only area. So the resistance of the circuit is going to increase actually by changing out this resistor. Weird, isn't it? You'd think removing a resistor would decrease resistance, but because resistor 5 was in parallel with resistors 6 and 7, removing it actually decreases current. So if we have more resistance, then we're going to get less current. If we get less current along this path, that means I4, 6, 7 is going to be less than what I4, 5, 6, 7 was. If we had made an equivalent resistor out of all of this, then it would have gotten, we're going to have less resistance on that chunk now. Now, if we had had this in isolation, I think all of this would be correct, but we're not in isolation. So we got to go a little bit further before we really commit to these ideas. We have figured out that between here and here, the resistance is lower afterwards than it would be before. Excuse me, the resistance is higher afterwards than it was before because we removed a resistor in parallel. So if this resistance is higher, that means that we've got from, let's say, A to B here, we've got the same resistance down one path, and we've got more resistance down the other path. So that's going to increase slightly the resistance of all of this chunk from A to B. Since the resistance of all of this will increase slightly, that means that the resistance of the whole circuit will be increased slightly since it's in series with R1. And R1 will actually get a little bit less voltage than it did before because this chunk has higher resistance, so it gets a bigger share of that total voltage. That's also consistent with our idea that current should decrease. If the current decreases here, that current is part of the total. So the total current through resistor 1 should decrease, and it will get a little bit because it has less voltage applied to it. So let's go to FET and see if we can model that. So we take resistor 5 and we remove it. So total current was, got to remove this from the last one. Reconnect, there we go. Total current was at 0.5 amps. If we remove resistor 5, total current went down slightly to 0.48 amps. Now, when resistor 5 was there, got to change its resistance back to 5, there we go. When resistor 5 was there, the voltage across the 10 to 2 ohm resistor 4, 6, 7 was 3 volts. But if I remove resistor 5, that voltage is actually affected. That voltage actually goes up a little bit. And if you think about why, it makes sense. The loop from resistor through resistor 1, 4, 6, and then 7 had a certain amount of current flowing in it. And with that amount of current, the voltage consumed really was dependent on the resistance of each one of those chunks. Well, by removing resistor 5, it decreased the amount of total current slightly. However, by increasing the resistance of this chunk gets a larger share of that total voltage. That's an interesting way to think about it. I think what you can see is you got to do more than one of these to really start to get your head around how to reason through it. I've purposely picked a pretty complex one here to show you that your initial kind of gut might not be right. You really got to think about, what if we make this change? What effects does that have locally? And then what effect does that have in the whole circuit? So let's go back to this 4 ohm resistor. Remember, it was getting 1.99 volts. Now it's having applied to it only 1.91 volts. Really, if you think about it, that's because between here and here, it was only getting 3.01 volts because the resistance of this chunk was a little smaller when resistor 5 was here. And so this chunk, being in series with this resistor, gets a smaller share of the total voltage if its resistance is smaller. With resistor 5 gone, the resistance of this chunk is actually larger, so it gets a slightly larger fraction of the total voltage. So even though total current went down, which means the voltage applied to resistors that get total current must have gone down, the voltage applied to this chunk of the series actually went up because the resistance of this chunk of the series went up. Again, we can always just take that to the extreme, right? If the resistance of this chunk went way up, then we'd expect that it's going to get a much larger share of the total voltage. Now you can see it's getting 3.65 volts, and this resistor would be down to a very small fraction, a much smaller fraction is 1.35. So use that, taking it to the extreme, to kind of reason through what's going to happen. Sometimes it's a good shortcut to the logic. All right, so with that, I think you've got enough to start trying the problems that are in the lab, 11 through 13, that ask about what happens when resistors are added in places. And if you want more practice, going back to the webcam here, the last slide of these notes has a problem that you can solve and some logic questions about some Newton lights and about incandescent bulbs. And there are some more practice problems on this website at allaboutscircuits.com. These are significantly harder than AP1, so it would really only be for funsies that you'd go down this path. Some of these problems are very, very challenging, but if you're enjoying this sort of thinking and you don't have a whole lot to do, if you're stuck at home, feel free, jump on that website and take a look at those. But certainly, these are not assigned. These are for extra practice should you need it. All right, good luck. Enjoy. Talk soon.